Okay, this is Dr. Williamson solving a problem. It's a buffer problem. It says calculate the pH of a 0.5 molar acetic acid, 0.5 molar sodium acetate buffer solution after 100 mils of 1 molar sodium hydroxide is added to 500 mils of the buffer solution. Okay, so initially, here's my 500 mils. What do I have floating around in my 500 mils of buffer solution? Well, mostly water. Then I have my weak acid, acetic acid. And then my sodium acetate is NaCH3COO minus. When you drop this into water, it separates into sodium ions and acetate ions. Sodium ions and acetate ions. And because it's a 1-to-1 proportionality between sodium ions and this, and acetate ions and this, whatever the concentration of the sodium acetate solid was, whatever you calculated it to be when you drop it in, that's going to be the concentration of your sodium ions and your acetate ions. So when it says 0.5 molar sodium acetate, that's code talk for 0.5 molar acetate ions solution, acetate ions. Also 0.5 molar sodium ions, but it's a spectator ion, and we're not worried about that in our calculations. Okay, so let me get rid of that now, so we know what's going on there. Whoops, didn't intend for that to happen. Okay, so let me erase this stuff. All right. Now, when we drop in 100 mils of sodium hydroxide, and it's 1 molar, what are we dropping in there? Here's my little circle here represents the 100 mils of 1 molar sodium hydroxide. That should be 1.0, but whatever. What's in there? It's mostly water. And sodium hydroxide separates into sodium ions and hydroxide ions. And if it's 1 molar sodium hydroxide, because it's 1-to-1, I end up with 1 molar sodium ions and 1 molar hydroxide ions. So when I drop this in here, I'm dropping in water, and then dropping in sodium ions and hydroxide ions. Okay, and the concentration is 1 molarity hydroxide ions. So what's doing the reacting? Well, the hydroxide ions are going to react, that's the base, is going to react with the acetic acid ions. So the reaction I'm going to have is CH3, COOH, aqueous. I'm not going to write the aqueous here for the sake of clarity, plus the hydroxide ions. That's how you know what's going to react. The hydroxide ions are not going to react with the acetate ions, because there's no, this is a negative and that's a negative. They're not going to like each other. And there's not a convenient H to pull off there, not a slightly positive hydrogen to pull off. And this is going to react. And we're going to make CH3, COO minus, that's sloppy, OO minus, plus water. Okay, now I have to make a BAA chart before, add, and then after or end. Okay, this is always in moles. How many moles of acetic acid do I have in here before I dropped in anything? Well, it is 500 mils, which is half a liter. And its concentration happens to be 0.5 moles per liter, which will give me 0.25 moles. So this is 0.25 moles. This is before I drop anything in here. I do have some hydroxide ions in here, but the number of moles of that is so small. Okay. How many moles of acetate ion do I have floating around in here? Well, it's 500 mils, and it's also 0.5 molar. So the math conveniently is going to be the same. Coincidentally, it's 0.25 moles. And this is, squiggle that out. What did I add? Okay. I'm going to erase this to, ooh, I don't know what I, okay. Okay, I still have that information elsewhere. What did I add? I added 100 mils of 1 molar sodium hydroxide. So that's 0.100 liters of 1 mole per liter of sodium hydroxide. But I know that for every 1 mole of sodium hydroxide, I get 1 mole of hydroxide. So I could say 0.1 moles of hydroxide ions. So I didn't add any of this stuff, and I didn't add any of that. And this is going to be 0.10, 2 sig figs. Okay. Now what happens? What I have afterwards? What I had, this is what you have to remember. See this arrow? This arrow means the reaction goes this way, right? Well, what happens is this consumes that. This gets used up by that. This is going to be 0.25 minus the 0.1. So this will be 0.25 minus the 0.1, because it's a 1-to-1 proportionality. And afterwards, I will have 0.15 moles of this stuff left. What about this? Right? This consumes that. This arrow means produces this. Right? How much of this was consumed? 0.1. That means 0.1 of this is created because it's 1-to-1. So this is going to be 0.25. And 0.1 of this was used up. So that means 0.1 of this is made. So when I'm done, I'll have 0.35 moles. Okay. So let me kind of erase some stuff to keep it clean. Right, erase that stuff to kind of keep it clean without erasing too much. And I'm going to erase this stuff. I hope I don't need that later to clean it up a little bit. Now to calculate the pH, I need the Henderson-Hasselbalch equation, which is going to be pH equals pKa plus the log of A minus over HA I need the pKa value. This is acetic acid. The Ka value is something you look up. I looked that up. The Ka value is 1.8 times 10 to the negative 5. That means the pKa is minus the log of the Ka value. And when I do that, I get 4.74. Oh, minus the log. Let me put that minus sign in there. Minus the log. I need this ratio right here, the concentration ratio. Well, I'm going to remind you of something I told you. The pH will be 4.74 plus the log of, now the A minus ratio will be 0.35 moles divided by, to get the concentration, it's got to be divided by whatever volume that it's in. Right? The moles divided by the volume. We agree on that. And this concentration at the end will be 0.15 divided by whatever volume that it's in. But since I had that picture over here, they're both in the same container. That means whatever the value of the volume is, right? I had 500 mils to start, had 600 mils. I had another 100 mils when I added the 100 mils here. 600 mils, I don't even need to calculate the concentration because I know that this volume will be equal to that volume. I know they cancel out. So I can just use the log of 0.35 over 0.15. So this will be 4.74 plus the log 0.35 divided by 0.15 will be 2.3. Take the log of that, add 4.74. And when I'm done, I get a pH value of 5.11. I didn't have to go to the step of calculating the concentration here and calculating the concentration here because they're both floating around, A minus and HA, they're both floating around in the same volume. So I know these volume terms cancel out, so I can just use the mole ratios. And so when I'm done, the pH went up, it became more basic, which makes sense because I added base to it. So it resisted change in pH. It changed pH a little bit, not a whole lot. Okay. Anyway, that's how you do those kinds of problems. I hope that helps.